Chemistry stuff on the test, right? Learn objectives. So please don't get crazy on the chemistry stuff. Because again, where are we not right now?
In chemistry.
We are not in chemistry, right? There's a reason why you guys take Gym Bio or Gym Gel. Not a chemist. Last time I took the chemistry course, maybe 2001. Yeah. So. Right. This is generic stuff. This is for the freshmen. This is very, very generic stuff. Just to make sure some of these guys are seniors and haven't taken a chemistry class in like 3 years. They took Gen Chem and they've been avoiding it as much as they can, and they're not going to take that. Oh, I hope you took organics. That's fine. Some of them maybe wait until taking out. I just got to make sure, right? I consider this a self-study chapter. It's just we're just going to touch on some things just to make sure. Oh no, Laura's looking at me like a crazy. She was probably one of them. You angry at chemistry? Me too. Right? Protein structure, nucleic acid, amino acid, right? I'm just making sure that for whatever reason you guys aren't getting turned around by some terms, that you can still recognize some of these macromolecules that I made you learn in Gen Bio. And, oh my gosh, every now and then you guys do something weird with acid and bases. You'd be surprised. Apparently not. He was like, nope, seen it. I'm sure you've had some classmates ask you some really odd stuff. You're just like, really? Right. Covalent bond, hydrogen bond, yes, for good bond.
Yes.
Bonds.
Yes.
Okay, the signal is just going to be tugging your earlobe twice. Like I'm ready to just like go over some of this. Oh, someone with the like double push of the glasses. That wasn't the signal. I like it. We'll save that one for another signal. Sharing electrons versus stripping away electrons, taking an electron, right? Sharing them evenly and unevenly, right? You guys should be able to differentiate between a covalent bond and a hydrogen bond and an ionic bond and a polar. Oh my gosh, she's laughing. She's like, I did this freshman year in high school. Synthesis reactions, right? We think about anabolism and metabolism, right? The whole metabolism thing doesn't go away because we're in a biology class. Matter of fact, we care about metabolism. I'd say more in a biology class. We just don't care about the chemistry of it. Right? Taking those smaller molecules, right, in that anabolic reaction and generating larger, more complex molecules, right? We're going to have to build macromolecules, right? You're going to see synthesis reactions. You should understand what those are when you see them versus these decomposition reactions of metabolism, these catabolic reactions where we take these larger, more complex molecules and we're going to break them down to their smaller components, right? We get to metabolism and we care about nutrients and those sorts of things, right? You're going to take these things up in the cell, you're going to break them down to their small components, and then you're going to build the macromolecules you want in that cell with those components. Again, you're going to see them over and over again. Acids and bases. Will, you want to help us? Acids and bases. Me either. Right, acid, that's our proton donor, right? This is going to dissociate, so we get this anion and this proton versus that base. Right, this is going to be our proton acceptor. Right, this may be dissociate here. This is cation. Right, as we get that higher number, that's the more basic, more alkaline versus the lower number is more acidic. Right? And every now and then I was like, I'm just going to give me on the test. Like, what's a neutral pH? 10.
Oh.
Right, neutral pH 7.
That one on there.
Right, we care about these things, so, right? Especially in biology, most of it we like. Why do we like phosphorus anyway? Right? We like that. We start changing the pH. We start changing our hydrogen acceptors and donors. We start changing the structure of these macromolecules, right? We start disrupting structure. We don't want to disrupt structure of your cells, all those molecules in your cells that you need, right? We don't want to start disrupting protein structure. We don't want to start disrupting DNA structure, right? That's what we have. That's what the body works so well as a buffer, because we like being in that neutral pH. We don't want things to influence pH in the body. Right? That's why a lot of these pathogens like neutral pH. It's not that they actually like neutral pH. That's why they happen to be so good at infecting your body. The organisms that like, high and low pHs don't like being in your body. The ones that like that neutral pH, that 7.4 pH, really like your body. It's a wonderful environment for it. It's going to make you sick. Macromolecules, lipids, carbohydrates, nucleic acids, proteins, right? I talked to you guys about all these things in Gym Bio. Lisa's going to tell us all about them because she remembers every word from Gym Bio. Right, remember all these things, they're building blocks, right? We get them as monomers, we can start constructing really large macromolecules with these as polymers, right? Lipids, we can just get rid of a lot of these. We don't get waxes and steroids in prokaryotic cells, so we don't really care about them in this course. Right, we will see phospholipids. We do see fats, and we don't really talk about it as fats when we talk about prokaryotic cells. We certainly care about phospholipids, right? We certainly care about structure, right? That lipid tail. Remember, we had our saturated, unsaturated. It's going to come up again when we talk about cell structure, which is the next lecture. Right? That saturated tail is it's saturated with those hydrogen bonds, versus we have double bonds, it's unsaturated. We can get polyunsaturated, right? We can make multiple double bonds. That double bonds closer, we're going to get that fixed angle on it, so it's going to get that little kink. But when you get that little kink, these things can't line up next to each other as closely. So you don't have van der Waals interactions, or at least not as many. So this is more fluid versus it's going to be more rigid. Right? We start caring about these sorts of things when we start talking about temperature ranges and what temperatures a microorganism can grow in. Right? So phospholipid is a lipid, that's not phosphate group. That organic group is going to change based on the organism. Right? That's why no one ever tells you about this organic group. They just say organic group. Right? That's going to change even with species and strain. Carbohydrates, molecule composed of carbon, hydrogen, oxygen, right, always in the same ratio. Carbohydrate, we can get a lot of functionality out of carbohydrates. Right? Long-term energy structure, or storage, we talk about in terms of being ATP, backbone of our nucleic acids, we can convert them into amino acids. We're going to see in things like peptidoglycan in the cell wall. Right? We can see them in signaling molecules for communication. Right? So carbohydrates, we're going to see them serve lots of purposes. See them as that monosaccharide, disaccharide, or even polysaccharide. Oh yeah, now it's starting to come back, right? To Gym Bio, and we did that first day stuff like, hey, you got to find them class. And you guys were like, oh, it's so easy. And I said, alpha, beta conformation, stuff like that. Right, typically we think carbohydrates being cyclic, right? They're not always cyclical. A lot of times in biology classes we see these cyclic carbohydrates. Right, monomer just means it's that individual one, disaccharide, let's move those two together. Because again, that was that, anabolism versus metabolism, right? This was the more complex macromolecule. We split this sucrose into a glucose and fructose versus we can take that same glucose and fructose and combine them during that sucrose. That's that 1,4 linkage that you guys stressed out about. Yes, Will, they stress out about 1,4 linkages. I don't understand either.
I stress about it.
Excuse me?
I stress about it.
You guys doing okay? Okay. We're good. This is still self-review, or do we need to spend some time on it?
Wait, what's 1,4 linkage?
Right, because I don't even think I have numbered carbons out here, right? Carbon 1, carbon 2, carbon 3,
Oh,
carbon
yeah.
4.
Okay, we're good.
Right, carbon 5, carbon 6. So that was that one linkage, but remember that was 1, 2, 3, 4. So linkage between that carbon 1 and that carbon 4, that's our linkage.
Okay.
they're always trying to show, this is in 3 dimensions, the way these things project out. They're always trying to show you it in 2 dimensions on paper. So that's what they're trying to show you about each particular line, is they're trying to show you the different planes. And so essentially, this is projected out in the opposite plane of that. We're just going to say oxygen. It would be based on that carbon. We don't really want to worry about that. If this is in that opposite orientation from there, it's just showing you that it projects out in the opposite planes. And that's our alpha linkage versus, now if this was going up the other way, that'd be our beta linkage. I don't need you all to differentiate between alpha and beta linkages in here or anything like that. Right? That's how our carbohydrates are assembled, are these alpha beta linkages, or these 1,4 linkages. Anytime we start seeing anything other than that 1,4 linkage, we start referring to that as branching. And we start branching these polysaccharide chains, where we just take them and we do that 1,4 linkage, 1,4 linkage, 1,4 linkage, 1,4 linkage, 1,4 linkage. Anytime we start having branching, that just gives us additional structure. Right? This is all 1,4 linkage. This is unbranched. This is branched. This has a lot of branching. Right? But if we think of this back with our cell wall structure, you're providing more anchor points of more rigidity. Right? You're getting more rigidity out of that structure. Right? That's when we really start seeing branching, is when we're talking about carbohydrate as a structure, not when we're talking about carbohydrate as energy storage and those sorts of things. Mainly one of the reasons we talk about any of this chemistry stuff is so when you see an image like that, you can interpret what in the world they're trying to communicate to you with that illustration. No, I actually care about the chemistry of it because I'm not a chemist. Right? But that illustration in that textbook is there for a reason. There's something they're trying to communicate to you. Right? And so really what I want is for you guys to be able to look at that and tell what they're trying to communicate to you. Why did they think that was important enough to put an image of it in the book? Right? Yeah, they're just trying to show you this is a branched polysaccharide, right? This is probably some sort of structure. You guys got really, really quiet. It's making me nervous. You guys doing okay? Mm-hmm. So the other part you guys freaked about in Gym Bio, I don't know why. Including that inside the macro. Thanks for sitting up close for this time. Right, nucleic acids. Right, our DNA and our RNA, nucleic acids can serve as genetic material. In general, when we're talking about life, we're talking about DNA as genetic material. This is a micro class, so we have to put that little caveat here and talk about nucleic acids because we can see RNA serve as genetic material in viruses. Typically, we see DNA as carrying instructions for the synthesis of our RNA, and RNA serving as our template for protein synthesis. Right? We can also see DNA control transcription in the cell in terms of promoters and regulatory cells. Right? RNA template for protein synthesis. We're also going to see RNA as ribozymes. Right? RNA now have enzymatic sites and can function as an enzyme. Right, adaptive molecule, our tRNA structural component. Right, and that was one thing we talked a little bit about in Gym Bio. Right, now that we have that 2' hydroxyl, and we have increased bonds that we can form, we can actually see RNA take on structural features. Right, and that's how we get it. Ribosome RNA, that's a structural component of that ribosome. Right, it's really because now you can start getting tertiary structure out of that RNA with that extra bond. Right? Our whole conversation was taking monomers and making polymers, though. So nucleotides, those are going to be those individual monomers of DNA. Right? So nucleotides will be our phosphate. It's going to be our pentose sugar. It's going to be our nitrogenous base. Right? Now, pentose sugar is either going to be deoxyribose or ribose, depending if we're talking about DNA or if we're talking about RNA. We're going to have one of 5 cyclic nitrogenous bases. Right, pentose sugar, there's our phosphate group. We're going to have to add in one of these nitrogenous bases. Right, G's, A's, T's, and C's. Please, nobody look at me like I'm crazy for saying G's, A's, T's, and C's. Everybody still with me, kind of? Spencer? I can't tell if that's like, oh my gosh, I can't believe we're still talking about this, or oh my gosh, I can't believe we're talking about this. How did the guy figure out? Alright, purines, pyrimidines. Years ago, Jim Bio told me they remembered it because TCU, they were pyrimidines. Their campus was nicer than ours, it's like a pyramid.
That works.
Someone else told me that the purines, they're bigger, and Texas A&M's campus is bigger, and they're the Aggies. I thought it was pretty good. What did you say?
I don't know anything about Texas schools. I'm from Missouri.
Oh, wow.
I didn't even know where Dallas was. When the hurricane came, I was like, are we okay? Do we need to move? We're like, you are not from here.
Oh my God. Pretty big state. This is a pretty big state. Right, 3 hydrogen bonds between the C's and G's, 2 hydrogen bonds between the 2 T's and A's. If we're talking about RNA, we're using A's. Somebody's pointing at their watch, so we'll come back and talk about the fact that these things are complementary and they're anti-parallel. And we'll talk about this 5' and 3', which again, for whatever reason, gave you guys fits into bio, and hopefully makes perfect sense to you now. All right, so we're going to quickly get through the rest of this and to get back and make sure you guys know what an amino acid is and actually know what protein structure is. And then we're going to talk about cell structure, okay?
They pointed the camera up to the ceiling. What did you guys do?
I didn't touch it.
That was just mean.
You want me to like track you as you're walking?
No. We were somewhere around here.
Yeah.
What is that? Nucleotides. I was putting you guys to sleep, right? No. I mean, I was hoping you'd be like, oh, DNA, we already know about all that. We talked about it in Gym Bio. Right? Some of these slides look really, really familiar. Right? Phosphate, pentyl sugar, right? Deoxyribose, R-ribose, 1 and 5. Estrogen bases, talk about pyrimidines versus our purines, right? Our T's, our C's, and if we're talking about RNAs, our U's, our A's, our G's. Again, I'm hoping that all of this is review. That's why I'm going through it a little quickly. Right, again, pentyl sugar, our phosphate group, one of these 5 nitrogenous bases. Right, remember our triple hydrogen, 3 hydrogen bonds between our C's and our G's. Right, 2 hydrogen bonds between our T's and our A's. If we're talking about RNA, our U's and our A. Right, DNA is going to be double helix. Most cells, most viruses, we will start to see DNA as a single helix in some viruses. Remember, our strands are anti-parallel, so I think that's where we left off. Right, this is where you guys looked at me like I was crazy in Gym Bio. So you should remember 5' and 3'. That's how I knew we were going to work. 5' and 3', 5' and 3', 5' and 3', 5' and 3'. Oh my gosh, guys, come on, 5' and 3'. Right. Right, DNA, our directionality, we go from that 5' end to that 3' end. Whenever we're talking about DNA, we're looking at DNA, we go from 5' end to the 3' end. Right, that 5' end, we're talking about that 5' phosphate. That 3' end, we're talking about that 3' hydroxyl. Because as we polymerize DNA, as we synthesize DNA, as we grow strands of DNA, we add incoming nucleotides to that 3' end. So it literally grows 5' and 3'. Everybody in here took organic, or maybe they didn't take organic, and we're not even going to worry about all those rules about numbering carbons, because that's for a chemistry class, and this is not chemistry class. And we know that anytime we look at this pentyl sugar, that this is always going to be carbon 1, this is always going to be carbon 2, this is always going to be carbon 3, this is always going to be carbon 4, this is always going to be carbon 5. Right? And that's what the world we're talking about when we're talking about 3' and we're talking about 5', right? These are prime carbons because that nitrogen is base, or the base. These are carbons too, and those are actually 1, 2, 3, 4, 5, you know. So the ones on the pentyl sugar are prime to distinguish them from what's on that nitrogenous base. Right? So when we're talking about 3' to 5', right, we're just talking about that hydroxyl that's off of that 3' carbon, this phosphate that's off of that 5', or that phosphate that's off of that 5' carbon. Right? Everybody feels good about 5', 3'.
looking for a couple more head nods. I'll say especially you because you were giving me that gym bio. Right, so 5' 3' in one direction, right, 5' 3' in the other direction, because DNA is, right, anti-parallel, right, not parallel, anti-parallel, right, so 5' 3' in one direction, 5' 3' in the other direction. So the whole reason we're able to get semi-conservative replication and maintain all the information we need in one strand. It's a fantastic, beautiful thing, responsible for, everything molecular biology. It really is. It's really, really interesting. Take molecular. We'll talk about DNA for like 3 or 4 lectures. Well, why are you shaking your head? You know it was interesting.
I love DNA.
Me too. Right, amino acids. Only thing I really care about there is this peptide bond. The peptide bond is a partial double bond. Sometimes it acts like it's something in between a single bond and a double bond. With that single bond, you get free rotation around that axis. With this partial double bond, you get this fixed angle. When we start thinking about secondary structure, that fixed angle is why we always get either a beta pleated sheath or an alpha helix. Right? That's why I always assume those conformations, because this peptide bond is always at that fixed angle. Right? That's the only thing I care about. Right, have our central carbon, have our amino group, have our carboxyl group, right, and then we can have our side chain. Right, it's that side chain that's going to give that amino acid its unique properties. Right, other than that, every amino acid is going to be standard. Right, amino group, central carbon, carboxyl group. So our group is going to give it its properties. This is just talking. Again, this is not biochemistry. Right, we can split that in 4 categories: our neutral, nonpolar, neutral, polar, acidic, or basic. Right? We start talking about neutral, nonpolar. We're talking about carbon chains, aromatic rings. We're talking about neutral, polar. We're talking about hydroxyl, sulfurhydryl, amide, and imidazole. Right? We're talking about charge. It's going to be something that has a charge on it. Right? For the biology majors, have you start separating out those R groups? That way in your head, it's going to be a lot easier for you to start learning these. So we're not here, like I said, we're just talking. Since we said amino acids, we're going to start a little bit about amino acids. If you are able to start separating them out into neutral, nonpolar, charged, neutral, polar, right, you're going to be able to learn them a lot more quickly. Right, and you got to draw them out or list them and all the things, you're going to be able to do a lot more easily because you're going to know that, oh, I'm looking for something that's aromatic, or I'm looking for a carbon chain, or I'm looking for an amide group, right? Because you're going to have to learn it, and you're going to have to learn it again, and then you're going to have to learn it again. If you go to graduate school, you're going to have to learn it again, and you're going to have to learn it again. I'm not joking. It's one of those things. After the 4th time, I just finally gave up and decided to actually learn them instead of memorizing them. So just do yourself a favor and learn them when it shows up in biochem or whatever class it shows up for you. Please do not go memorize all this stuff for the exam, because every now and then I get to the last page of the exam and on the back somebody has drawn all of this out because they're angry because they wouldn't study it all because they thought it was going to show up and it didn't show up. Right? I'm not asking you about R group. I'm just trying to make sure that you understand what an R group is. Right? So we were talking earlier about monomers versus polymers, right? These individual amino acids, we start putting enough amino acids together, and then we're going to have a protein. Right? So we have our amino acids, it's that carboxyl group, and we're going to form that peptide bond with that amino group. And we're going to add these into our linear sequence. Right? It's literally going to give us our primary structure, the linear sequence of those amino acids. Right? So we have our amino acid here, they just got real generic and just said R, right? They didn't even try to pretend. Right? But we form that peptide bond with that carboxyl group, right? Forming with that amino, right? It's the same thing we talk about N terminus and a C terminus on amino acids, right? That last C terminus, we're going to attach something. We're going to actually N terminus of that incoming amino acid to it. We're going to extend that polypeptide chain as we're getting our synthesis, right? So when people start using that term peptide, They're just talking about these really short chains of amino acids. We're probably talking about 100 amino acids. It's an arbitrary term. People say peptides. Sometimes they're talking about 200. Sometimes they're talking about 5. But once we start getting larger than 100 amino acids in that polypeptide chain, we should probably just start calling that a protein, right? Some people are going to say it's not a protein until it's functional, right? Some people are going to say, well, once you get some functionality and you got a domain, it's a protein, right? These are all arbitrary discussions. I don't know. If you're just really passionate about the difference between a peptide and a protein, knock yourself out and have that discussion. I'm just trying to make sure you understand when you read peptide, people are just trying to tell you that's a short polypeptide, right? Probably not getting the full functionality out of a protein. Right, versus our protein, this is just our compound composed of amino acids. I'm saying globular, we think of it as being globular in nature or having that three-dimensional shape, right? And it's that shape, it's that structure that gives it its function, right? So you can see this be part of that structure. We may see its function as an enzyme. We may see it play a role in regulation because it binds to DNA or binds to another protein, helps with transportation of that cell. We're going to start seeing all sorts of different properties, including, for a microclass, roles in pathogenesis and immunology. A lot of functionality. But it's those individual nucleic acids, right, that are going to code for our amino acids. We've all talked about genetic code at some point here somewhere, right? So our codons, every 3 nucleic acids, right, every 3 base pairs of our DNA is going to encode for a specific amino acid. Right? Later, when we get to microbial genetics, we'll talk about open breeding frames and all those things. Right? But if your DNA says ACT, right? We think about what it looks like for RNA, and it's saying ACU, right? That ACU is going to encode for, a 3. So those individual base pairs and those nucleic acids, that's going to influence what our amino acid sequence looks like. Just like our DNA goes from 3', our protein is going to go in terms of C-terminus. That's because the sequence of our DNA is going to influence the sequence of our polypeptide. Right, protein structure, I think that's really, really close to ground. Stop talking protein structure. Right, that linear sequence of amino acids in that polypeptide chain, that's our primary structure. Right, as we look at those covalent bonds, those peptide bonds, and how they connect those individual amino acids. Secondary structure, we're limited to 2 types of secondary structure, our beta-pleated sheets and our alpha helix. Again, it's because of that angle of that peptide bond. It's either going to give you that little pleat or it's going to kink it around so that it forms, right, that helix. And it's actually the bonds that are forming along this backbone that gives you that twist of that, right? It's really that oxygen, that nitrogen, right, that hydrogen there, right, getting those little hydrogen bonds between this hydrogen and this oxygen, they're going to put you in that pleated pattern or that kinked helix pattern, right? So it's hydrogen bonds along this polypeptide backbone versus tertiary structure. Tertiary structure is when we start talking about the R groups, right? Secondary structure, we're not talking about R groups and their contribution. Tertiary structure, now we are talking about R groups, right? If we're looking along that polypeptide backbone for secondary structure, these are always really close in proximity to each other, right? Versus tertiary structure, now we can take that R group that's up here and we can bend this whole thing over and it can start forming hydrogen bonds with this one down here. That's how we start getting that globular structure, right? Now this is when we start getting unique structure because this polypeptide backbone, remember we said, it's our central carbon, our amino group, our carboxyl group, also the amino acid, all this looks the same. That's why that beta-pleated sheet is so uniform. That's why that alpha helix is so uniform. As we said, it's this hydrogen and this oxygen on that corresponding amino acid or that next one is responsible for that. So those interactions always look the same because this is extremely uniform. But once we start talking about tertiary structure and start talking about the hydrogen, the bonds that form off of that R group, now those start becoming unique. It's not just a matter of what amino acid is there. It's the sequence of amino acids that matter too. And what they're in close proximity what is this polar or non-polar, is this charged or uncharged, and all those things. Is it going to start forming ionic bonds, hydrogen bonds, that we're going to start getting hydrophobic interactions and all those things, right? So that's why we get this near infinite number of proteins, right? We add an additional amino acid, and all of a sudden, it wants to fold completely differently, right? Same polypeptide, we just add an additional one versus if we substitute one out, right? We start getting very, very different tertiary structure out of that. Versus quaternary structure is from separately encoded polypeptide chains. What's going on? You still feel good? You can say no. Okay.
So this is interactions between different proteins together. Is that what you mean? Or
We could get complicated on whether we want to call them different proteins at that point if they need that quaternary structure to carry out their function, but yes.
sorry, say that again.
We can get into some arguments on how we're going to define proteins. So, right, some people aren't going to call it a protein until you can get function out of it. A lot of things with quaternary structure, you don't get that function until you have that quaternary structure. So we don't necessarily want to call them two proteins. They are two polypeptides. So
Okay.
they are two separate tertiary structures that are interacting with each other.
That's what I was
There
asking.
was a polypeptide chain over here. It had its own primary sequence, or primary structure, its own secondary structure. It formed its own tertiary structure. There was another polypeptide over here with its own primary structure, secondary structure, tertiary structure, and those two structures interacted with each other, and that is quaternary structure. Separately encoded polypeptides, right?
Okay.
So alpha and beta are the primary structures and the secondary structures.
This is secondary. Alpha helix and beta pleated sheet are secondary structure. The linear sequence, right? Like when we go back here, right? We make that polypeptide bond. And this is that primary structure. That linear sequence, the order that those amino acids are covalently bound to each other.
What's the difference between the alpha helix and the beta sheet? I forgot, like, I know that the peptide one, like, it's like big or small, and it kind of affects the shape.
Ooh, we can start to get complicated. For the most, Will says no. Tell us. I'm going to say beyond the scope of this class. I'm going to go with Will. Really, the big difference is how they're going to fold and how they interact when they fold, and we get into all these weird things like are they parallel or anti-parallel beta pleated sheets, and so that changes how the other R groups extend out. Alpha helices is really more so the amino acids that determine which one they're in and what that means. If you're alpha helices, you may want to hide your hydrophobic amino acids in the interior of that, or you may take that and shove that in a membrane. So we tend to see different parts in different ways. If you're a protein that interacts with DNA, you'll take that alpha helices and insert that in the major groove, that sort of thing. You may want to lay the other one over the back, and you may do that with some charge residue so it can electrostatically interact with the negative charge for those phosphates. So there are, there's a difference in like how far they space out and how many angstroms and all these things, but unless you're a chemist, those things don't really matter. We're more interested in structure and what that structure is going to allow it to do. A beta sheet is going to do better to form like a pocket in an enzymatic site or a substrate site on an enzyme, that sort of thing.
Is a tertiary structure like when an alpha helix and like beta sheets that go back and forth together, like they bond together?
We're going to see alpha helices and beta pleated sheets interact with each other as part of tertiary structure. Yes.
And then it's separate of those come together and make quaternary.
Yes, separately encoded. Like two different things that have their own tertiary structure coming together. Will, you're not going to do it? You're not going to do it? You sure?
Yeah, you did a really good job.
I thought you were going to ask me about an antibody.
I think you did a really good job.
Because I don't think we have time, because you asked me about an antibody, I was going to have to run out the door, around the building, and back in the back door. It's quaternary. It's quaternary, separately encoded polypeptides. It's quaternary. Somebody else tells you differently in their class, use their answer in their class, but it's quaternary. Look it up. Quaternary. I'm going to skip this. This is just me rambling because I like regulation. I study transcription and translation. All these things are interconnected, but we'll save it for I probably will try to confuse you between a nucleic acid, amino acid, peptide, polypeptide, protein. So just make sure you feel good about those terms, because it's really weird when you guys go get this in your comps and you don't know the difference between a nucleic acid and amino acid. Got a whole lot of questions for you if that's a mistake. All right, cell structure. This is still recording.